Hello guys, so in this video we're going to do a continuation of our previous video about how to do convolution, erode and dilate in the FPGA using VIVADO HLS. In the previous video we lost probably half an hour just showing the theory what a convolution is and how to implement it in the FPGA in terms of what is a line buffer and what is a window and stuff like that. Okay, so today we're going to learn how to actually implement that in C or C++ code using VIVADO HLS. In this video we're going up to the point that we generate the IP core. In the next video we're going actually to use this on the Zinc. Hope you guys like it. If you like, give me a thumbs up and let's go to the board. So guys, just to remember what we're supposed to do, basically we're going to have an image, okay? This image is going to be transferred to our core through an axis stream, okay? Our core, we're going to have the following options. It's going to do a convolution, an erode or a dilate based on some parameter that you're going to transfer through axilite, okay? And you're going to have a result. In the lab, we're going to see that just by using the theory that we use, that we learned in our last video by using line buffers, we need to solve this issue here. The line buffers offset the image because they have a kind of internal delay. They will delay a little bit the results, and this delay will cause the result image to be translated a little bit in this direction here. Okay, and basically we're going to learn how to hold the stream a little bit. Okay, in order to have our line buffer fill to start to send the image. So the stream will come here, wait a little bit, then continue. Okay? I want to switch now to the lab part, to the code, for you guys to analyze the code and see how it works.
Hi guys, so let's start by analyzing the code, the C code that we're going to use to generate our convolution, erode and dilate IP core. Okay, so this is the prototype of our function. Okay, we have the input stream, okay, an output stream, okay, a kernel where you define which filtering operation you want to do, and an operation. So here, if it's 0, is going to be convolution, 1 erode, 2 dilate. Okay, these other functions here, okay, are just to be used as reference. Okay, functions, cool. Because when you use our test bench, we're going to compare the result of this guy with those here. Okay. These are actually functions that are used by our IP core. So let's move it. Okay. Here we are just the definition of the kernel size. In this case, is a 3x3 kernel. Okay, and these are just the images that we are going to use to exercise our IP core. Okay, basically to test if our test bench is doing what it's supposed to do. Okay, this is where we define the size of our image. Okay, and this is an important one. Is the header for using the HLS, the VIVADO HLS wrapper functions to implement line buffers or windows. Okay. So let's jump to the code. The code is quite simple. This the input stream and output stream will be declared as axis because they are axis stream. Okay. All the rest, the return of this function, this return just means that you're going to have a start and stop commands through the axilite interface. Okay. The operation and the kernel will be sent also through the axilite interface, and all of them are going to be merged in the same axilite interface. So these three guys here, okay, they start and stop, the operation and the kernel will be sent through the same axilite interface. Okay, here is where we define our line buffers and our window. Okay, as I explained in the previous video, the line buffer is imagine that is a line delay that is going to position our pixel stream in a way that is in a window. Okay, so we can just multiply this window by your kernel. This part here we are not going to take care now, okay? And this is the basically our code. Here is just a for loop that we iterate in our pixels, okay? In this case, 320 by 240 is 76. Let's calculate 76 something. Yes, 76,800 pixels, okay? Here, the pipeline pragma is used to improve our latency. Is basically is going to create this for loop in a way that while we are calculating the output of a stream, we are receiving the next pixel stream. So you really improve the speed of your IP core by using this guy here. Okay. So first thing, we read our stream, and by the way, this will block if there is nothing to be received. Then we get our pixel, and we start to put this in our line buffer. We do a shift up and insert top. This is basically going to populate our line buffer. Okay. While our line buffer is being populated, for sure in the beginning will just be filled by zeros because they start as zeros. We're going to basically multiply the result, what we have in our line buffer, with our kernel, and you do this for every pixel that arrive in our IP core. Okay, so basically we get a value from our line buffer and we multiply by our window. Okay, and we insert this result in this window object here that we created here as well. Okay, so basically this window here is the product between our line buffer, okay, and our kernel. Okay, then after this is done, what we need to do, okay, first we verify if our current position, if our window, our sliding window, is inside the image. Okay, remember in the previous video, in the theory, that I was explaining that it can be outside, and in this case, if it is outside, we just put zeros. Okay, and here you have a big switch where actually we switch between convolution, erode, and dilate. Just to remember, the convolution, we just sum, okay, all the values that are in our window. The erode, we're going to get the minimum value that is inside the window, and the dilate, the maximum value. By the way, they are implemented here. Okay, this is how we get the minimum value in our window. This is how we get the max value, and this is just a sum. Okay, we initialize an accumulator 0, and we just sum with every element in our window. So this is a convolution. Okay. This part here I comment out because I want to show you how it works. We're basically going to start. This is our test bench. I'm going to explain it. Let's explain it now. So what we do, we load a test image. Okay, we convert it to grayscale. By the way, our IP core works in grayscale. Okay, then we populate our stream with the pixels from the input image, and we call the function conv2d by hand, and in the end, and we save this image, okay, this result, and we call an IP core. The idea is that we need to compare, okay, to compare if the convolution that we did strictly in software did his job compared to, by the way, the opposite. We want to check if the IP core did his job by comparing with a reference. Okay, so let me just uncomment this, and we're going to run, and I'm going to show you the results. We first, first we're going to use the impulse kernel. Okay, is a kernel surrounded by zeros, and then the center you have a 1. This is basically a pass everything filter. It's going to keep the image as it is. Okay, so let's first run. Okay, cool. So he did it. Okay, so he loaded an image. He created call it a reference function and save the results into an image file. By the way, the results are where I define them. Yes, I define them here. Okay, in this directory here. It can be any directory. Okay, let me just open these images now. Okay, in my case they are here. Okay, let me put the two images side by side. Here, guys, I don't know if you observed, the left is the result of the kernel and the right is the original image. As we use our impulse, the results should be the same, but you detect that there is a kind of slightly shift, okay, between the original image and the result image. Okay, it seems that the image is slide a little bit in the right diagonal direction. Okay, this is caused by the first, these zeros here are just because our window will be outside. Okay, our window will be sliding like here or here, and one of the part of the window will be out of the image, so should be 0. We simply cannot calculate that. Okay, but this shift is wrong. Okay, and basically it happens because of the delay created by our line buffer. Okay, our as we explained it before, our line buffer is a delay of lines. So the first pixels that you put into the line buffer, they will not come out after a certain delay. Okay, and this delay is basically 2 lines plus 3 elements in our case of the 3x3 kernel. Okay, so first thing that we need to solve is this. We want to avoid to have this shift. Okay, so how we solve this? We come here in the code. Okay, we're going to comment this part and uncomment this. Okay, so basically this is just going to wait, okay, until a counter arrives to a certain value. Okay, call it wait ticks. Okay, maybe I should call wait pixels. Okay, call it whatever you want, but okay, wait pixels. So basically we're going to wait until our line buffer has a minimum amount of elements to start to output data. Okay, and by the way, our last element we put as 0 because we are not ready to finish our stream. Okay, by the way, you need this, otherwise when you use through the Zinc or through any other processor that uses a DMA to speak over IP core, the DMA will never know that the operation is done. So at some point we need to put this last here to 1, and this is where that should mark that our stream is finished. Okay, so we just uncomment this, and we uncomment also this part here. So as we are going to wait some time to start to stream the pixel results, and at the end of the loop we need to put down some zeros, okay, to finish our image. So basically if we wait like 100 pixels, at the end you need to give these 100 pixels back as a value of 0, otherwise your image will be half complete. Okay, by the way, how we calculate these wait ticks is here. Basically we have, as we have a line buffer of 3 elements, what we need to do, we need to get the number of the size of our line multiplied by our kernel dimension minus 1 plus kernel dimension divided by 2, which is 241 elements. Okay, so we basically going to wait 241 elements, okay, before we start to output something, and at the end we're going to output more 241 elements as 0. Okay, and then we mark our our stream to finish here. Okay, so let us just save this and rerun again. Okay, maybe now we launch the debugger. Okay, so as we mark it to debug, okay, we are probably here, so let's continue our debug. So this is basically where we start our IP core. Let's continue. Here is where we actually send all the data that we could, and now the part that we should send the remaining zeros. Okay, so basically we need to send 241 zeros. Okay, and in the last iteration we should send the last flag. Okay, so we continue here, and at the count with 240 we send our last. Okay, so if we continue here, should be done. Okay, and now if we load our image, okay, the Lena, the filter result. Cool. Now guys, we have this black border here, where is, by the way, where our window will be outside of the image, but we don't have anymore this shift. So for instance, the tip of the nose of Lena will be basically here as well. So maybe if I put something like this. See? So guys, this is basically our kernel working as expected. Okay, so let me go back to the synthesis again and comment it more. Okay, by the way guys, this is the part where we output our string values. By the way, is the output string dot write. Okay, and well, let's test something different now. So let's come here, we're going to comment out our impulse. Okay, and we're going to apply, for instance, the edge detection. Okay, so as you see here, we have surrounded by -1 a center of 8. So basically, if we multiply 8 by our biggest possible value, 255, you're going to be more than the 8-bit grayscale. So that's why we need to come back here. Okay, and for instance, divide by 8. By the way, if you want, you could put this division as a parameter in Axelite and change it as you want. So let's run again the simulation. We want to save. We don't want the debugger now. And let's launch it. Okay, so now let's open the image. So again, this is our input. This is our output. Okay, so it's basically what we want. This kernel actually do this edge detection. Okay, so I think it's in the Y. So basically we are enhancing the edges that are in the Y direction. Okay, so as our test bench at least is working in C, I think it's time that we could check if the synthesis is correct. So let's just click synthesis and see if the VIVADO HLS is able to create an IP core from it. Okay, I just pause here and come back again when it's done. Cool, so VIVADO HLS was able to synthesize without no error. Okay, so the latency here, which is the total time that we need to calculate our convolution, erode or dilate, is actually this number here. This in nanoseconds is basically this divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5. yes, 691 microseconds. This is this is really fast for convolution, guys. I think it's faster than a computer probably. I did some tests with OpenCV, and for kernel 7x7, I think we are like 3 or 4 times faster than a normal dual core, actually quad core Pentium computer. Okay. So maybe a last point that you could test is to verify the co-simulation. Okay. So let's use model sim. We want to dump trace because we want later to see the signals. Okay, so let's run it. So basically now we are asking to simulate the generated HDL code with our image and verify if the results are okay. So the co-simulation worked. Okay, so our result is basically the same. So means that the generated code did what he's supposed to do. So we can use this IP core, we can export it to Vivado and use on the Zinc, for instance, or in the microblaze. And basically is what we're going to do in the next video. Okay, if you come back here in cast a scene, let me just put here the window a little bit better. So yeah, he did. I will not lose too much time seeing the waveform, but basically, guys, that's it. This is what you need to do to implement a convolution, an erode, and a dilate in an FPGA using VIVADO HLS. I hope you guys enjoyed. I'm going to put this code available on a Google Drive address or something like this, so everyone can see how it does. Check by yourselves. If you want to, if you don't want to wait, you can already put this IP core and test in your Zinc. And any doubts or other ideas on other videos or something like this, you guys just contact me and tell me more or less what you guys want. Okay, so hope you guys enjoyed. Give me thumbs up if you liked, and see you guys in the next video.